So far we've seen the effects of electrons as they move between energy levels and they jump, and we see the energy released in the form of light. Today we are going to talk about where are those electrons exactly located in the atom and see all of the different mathematical configurations that scientists have figured out about those tiny little electrons. It's pretty amazing. If you'll remember, Erwin Schrödinger was the one who came up with this idea here of the quantum mechanical model of the atom, which basically gave us a whole lot of ideas about electrons. They don't go in orbits. They are in different areas called orbitals. So this first guy up in the top left, this is Niels Bohr. Remember, he's the one that said, hey, these electrons circle the nucleus in these paths or orbits. And the atoms have fixed energy when the electrons are here, which means different electrons could live in these different levels based on the amount of energy that they have. He wasn't totally right about the orbit part, but he was totally right about the energy. And then we've got Louis here with his mustache, and he basically was talking about that particles could also behave like a wave. If light could be a wave and a particle, well then a particle could be both a particle and a wave. And so he was more concerned about this space beyond the nucleus, what's happening out there. Here's Werner Heisenberg. He says we can't know both the location and the speed of an electron at the same time. It's called the Heisenberg uncertainty principle. You can know the speed, you can know the location, you can't know both at once. And here's good old Erwin, and he mathematically proved the location of an electron in a 3D region outside of the nucleus that we call orbitals, and we're going to talk a lot about that in just a minute. So the first thing that you're going to want to write down on the back of your orbital diagram, your atom diagram, I would take some decent little notes back there. Don't write everything down, be brief. So this first big fancy thing that we're going to talk about today is called the principal quantum number. The principal quantum number is a very fancy way to say energy levels. When you get to college, they will be more specific about these principal quantum numbers, and there's magnetic quantum numbers and spin quantum numbers, but in high school chemistry, we just need you to know the terminology. We don't get down to the nitty-gritty details like they do in your freshman chemistry class. So the principal quantum number for an atom is designated by N. That's the symbol for principal quantum number. The highest number of energy levels that an element can have is 7. So anytime we draw a board diagram, we're never going to draw one with more than 7 rings. There are no elements out there with more than 7 rings. So all we've effectively done just now on this slide is renamed energy levels and told you that we call them the principal quantum number. If you flip over to your atom diagram, I'm warning you now, there are a ton of formatting errors when I transfer this over to make it a PDF. It made all my numbers in a wacky spot. So kind of ignore all of this and let me fill it in with you so it makes better sense. So basically what you're looking at is the energy levels that are outside of the atom. And so this is energy level 1. So if you look over here where it says N equals, out to the side of N equals, let's label each energy level. So this gray part in the middle is the nucleus. And so from the nucleus out to the first black line here, this is the outside border of energy level 1, or principal quantum number of 1. So we're going to go ahead and label that with a 1. Then we're going to go and we're going to do the same thing for all the other energy levels. This is energy level 2. Level 3, level 4, level 5, level 6, and level 7. So my numbers just didn't line up right when we formatted. So there are 7 energy levels, and there's no element out there with more than 7 levels. Now we need to figure out how many electrons can fit in each level. We talked about this a little bit at the beginning when we were making our board diagrams for the hallway activity that one day. But now we're going to teach you how to do it for all of the energy levels, and you don't necessarily have to memorize all of the numbers. All you have to know is that you can use this little equation to find your number of electrons. It's 2n squared. I would definitely write that in your notes. N represents which energy level you are in. So if you plug in a number for n and solve the equation, you can find out the number of electrons for each level. So for example, when n is equal to 1, we would do 1 squared. If you remember PEMDAS, we're always going to do our exponent before we multiply. So 1 squared is 1 times 2, and that gets us 2 electrons. We can do it again. 2 to the second level squared. 2 squared is 4 times 2, and that gets us 8 electrons. For the third level, 3 squared is 9 times 2 is 18. So you should remember those numbers from middle school. Well, what if we did maybe the 6th level? The 6th level is 2 times 6 squared. 6 squared is 36 times 2, and that gets me 72 electrons. So go back to your atom diagram, and we're going to fill in the electrons. So down at the bottom where it says 2n squared, we're going to put 2 electrons in energy level 1, 8 in energy level 2, 18 in energy level 3, 32 in level 4, 50 in level 5, 72 in level 6, and 98 in level 7. So within each energy level, we have something called a sublevel. So it's just a different zone in that level where we know that the electrons are. And this is where it becomes very patterned and very regimented, and it's kind of interesting if you stop and think about it at the end. So we start filling up sublevels from lowest energy to highest energy. So electrons are going to go into a sublevel that it's easier for it to get to. And we have 4 of them. The lowest energy one is called the S sublevel. Then we have the P sublevel, the D sublevel, and the F sublevel. My second year teaching, somebody looked at that and said, super powerful duck farts. And I was like, what? And it kind of stuck. And so that's what we call them. So the 4 sublevels within an energy level are called the S, P, D, or F sublevel. So within the principal quantum number of 1, or within the first energy level, we have 1 sublevel. We call it the 1s. When you go down to the second energy level, there are 2 sublevels. It's called the 2s and the 2p. In the third, there are 3 sublevels: the 3s, the 3p, the 3d. And the fourth level is the 4s, the 4p, the 4d, and the 4f. So what happens when you get to the 5th level? You get to the 5th level, and we've used up our SPDF. There isn't another letter. So there are these theoretical orbitals where electrons could go, but we don't actually have any atoms that use them. And so we made up some arbitrary names for them, and we call them the G, the H, and the I. We don't ask you about them. We don't focus on them. We really just focus on the SPDF. But so up here at the top where it says sublevels, in the first energy level, we call it the S. The second energy level has an S and a P. The third level has an S, a P, and a D. And the fourth level has a super powerful duck fart. So all four. Then we get to the fifth, and we have our S, P, D, and our F, except there's that weird one. We're going to call it G. And then our sixth level has an S, P, D, and F, and it also has a G, H. And our seventh level has our SPDF, and it has a G, H, and an I. So let's think about how many electrons are going to fit into each of these sublevels. If you think about it, in the first energy level, it holds 2 electrons. So this S sublevel up here must be holding both of them. So the S sublevel can hold a maximum of 2 electrons. It can have 1 or it can have 2. So under all of your S's, you can put a 2. Then, let's think about it. In the second energy level, it can hold a total of 8 electrons. Well, if 2 of them are in the S, the remaining electrons are in the P. So the P holds a maximum of 6, because 2 plus 6 is going to get me that 8. So all of your P sublevels hold 6. Then I go to the third level. If the third level holds 18, the S and the P combined have 8 of those, so that means the D must have the remaining 10. So the D sublevel holds 10 electrons. So we go to the fourth level. The fourth level holds 32. 18 of them are here. And so if we subtracted, that gets us 14 in the F sublevel. At this point, hopefully you see the pattern. It's going up by 4 electrons each time. So this is plus 4, this is plus 4, this is plus 4. And when we look at our G, H, and I, the G's can hold 18, the H's hold 22, and the I's hold 26. Sorry, it's hard to see. So when you add up all your numbers from the entire level, it should equal the total for that energy level. So these are sublevels. They're like little mini levels within each energy level. Then we have to talk about orbitals. Orbitals are kind of like a shoebox for electrons. Each shoebox can hold 2 electrons. So within each sublevel, we have these little shoeboxes that each will hold these electrons for us. So think of the number of electrons like the number of shoes. So if I have 2 shoes, how many boxes do I need? 1. 1. If I have 6 shoes, how many boxes will I need? 3. So 1, 3. If I have 10 shoes, I need 5 orbitals, 5 boxes. 1, 3, 5, 14 is 7. So again, it's another pattern. 1, 3, 5, 7, 9. 1, 3, 5, 7, 9, 11. And 1, 3, 5, 7, 9, 11, and 13 to hold all 26 of I's electrons. So if the numbers game wasn't weird enough, now we're going to talk about the shapes of these orbitals. It's something that I'd like you to add to your notes. Make sure that you wrote down the definition of an orbital as an area of space within the atom that holds 2 electrons. So when we place electrons into the s orbital looks like a sphere. So it looks like a circle. And so if we could put a tracking device on an electron and take a picture of that electron, all the red dots represent where that electron was every second. And so from that, we can figure out what the shapes of these orbitals are by knowing their location within their region of space called their orbital. So an S holds 2 electrons, so somewhere in there, maybe there's one here, and maybe there's one here, but there are definitely 2 electrons somewhere in there if we could take a snapshot. A p orbital. Now here's where it gets weird and mathematical, and scientists and mathematicians have come up with these 3-dimensional areas of space that are pretty weird. This guy is called dumbbell shaped. I think it looks like a propeller, so I remember P is for propeller. And so again, we might have 2 electrons somewhere in this zone. So if this is a p orbital, there could be maybe one here and one here. There could be one here and one here. There could be one here and one here. So this is a region of space that holds 2 electrons. This is the orbital. Now if you remember the p sublevel hold a total of 6 electrons. And so if I've got 6 electrons and this orbital up here only holds 2, I'm going to need a total of 3 orbitals to hold all 6 of those. And when we superimpose them on top of each other like this entire thing together is called the S sublevel. And it consists of a p sub x orbital, a p sub y orbital, and a p sub z orbital. So it's a 3D region of space where we can find all 6 of those electrons. So I need you to understand the difference between an orbital, which holds 2, and the entire sublevel, which will hold all 6. Let's get even weird. This is a d orbital. There are 5 different d orbitals. 4 of them look clover shaped like this. So in my notes I would draw a little clover with four leaves on it. But one of the 5 actually looks like this. It kind of looks like a P with a donut around the middle. You would have to ask a mathematician how in the world they came up with this. It's pretty weird, but we just say that a d orbital is clover shaped. Here's where people get confused. Don't forget, it's a region of space that can hold 2 electrons. So even though there's 4 regions, maybe there's one here and maybe there's one here. So that means you're going to have some regions that are just empty space, because remember, these electrons are bouncing around and moving around somewhere in that region. And so it's just a funky shaped region of space where we can find 2. Same thing up here. Maybe there's one here, maybe there's one here. Just a region of space. Then if we took all 5 of these and superimposed them, we would get some kind of crazy mathematical 3-dimensional shape that's way too complicated to draw. And then the F, they get really weird. To me, they look like a bunch of grapes. There are 7 different orbital shapes for the F orbitals. Still, region of space holds 2 electrons. So maybe there's one here, and maybe there's one here. And all of the rest of that space is empty until those electrons decide to bounce around somewhere in that region. So I thought this was a pretty cool picture. This shows you all the different orientations for all of the different orbitals. So you can see the S orbital here is a sphere. The P is that dumbbell. There's your X, there's your Y, and your Z. And then here's the D's that look like clovers with the one weirdo that looks like a donut. And then you've got your F's, which look like clusters of grapes, and then you've got kind of like this double donut guy right here. So these are all the different regions of space that can hold 2 electrons. I've never even seen a diagram for GH and I. Don't really talk about it because we don't use those guys. The easy part is when you put high heels into a shoebox, and maybe some of you have never done that, but when we put them into a shoebox, we always put them in so their heels are opposite. Well, that's kind of what the electrons are doing in an orbital. So if we're in the p orbital, that looks like a propeller, and there's one here and there's one here, we say that they are spinning in opposite directions. So if this one is spinning around like this, the other one is spinning backwards in the opposite direction. Thanks for joining me. I will clear up any misconceptions, and we'll talk a lot more about this in class on Tuesday. Have a great evening.